Hello, welcome to our CompTIA Security Plus course. In this lesson, we're going to talk about cryptography, covering some background about crypto systems, proven technologies and implementation, steganography, cryptography use cases, and cryptography constraints. So, a crypto system, right, or a cipher system provides a method for protecting information by disguising it in a format that only authorized systems or individuals can read. The use and creation of such system is called cryptography. Cryptography involves turning plain text into ciphertext, and then turning ciphertext into plain text. Specifically, encryption protects confidentiality and safeguards data integrity. Now, related to cryptography, an algorithm is a mathematical procedure or sequence of steps taken to perform encryption and decryption. You can think of an algorithm as a cooking recipe with the ingredients needed and step-by-step instructions. Algorithms are used in conjunction with a key for encryption and decryption. Now, the process of encryption is based on two different principles. First is to confuse, or by confusion, or to diffuse, or diffusion. First, let's talk about confusion. The plaintext input should be significantly changed in the resulting ciphertext. More technically, each bit of the resulting ciphertext should depend on the numerous parts of the key to hide any connection between the two, making it difficult to reverse from ciphertext to plaintext without the key. The second one is diffusion. If the plaintext is changed, no matter how minor the change, at least half of the ciphertext should also change, and vice versa. Like confusion, diffusion makes things more difficult for an attacker. Specifically, diffusion mitigates the capability to identify patterns that might help break the cipher. Keys. Cryptographic algorithms and keys work together. A key determines the output of a cryptographic algorithm and consists of a random string of bits. Keys used in cryptography provides for secrecy. In fact, a principle known as Kirchhoff's principle states that only secrecy of the key provides security. This is particularly important in relationship to the associated algorithms. An algorithm itself does not need to be kept secret. Depending on the type of algorithm used, either the same key is used for both encryption and decryption, or else yet mathematically related keys are used. Keys are also need to be of an appropriate key strength or key length to prevent brute force attacks. Key size is expressed as the number of bits in the key used by the algorithm. The longer the key, the more difficult it is to crack. When keys are generated, it needs to be done in such a way that the key contains enough entropy or randomness. Modern cryptography relies on random numbers. However, pseudorandom numbers are also commonly used so that the numbers appear to be random, at least statistically, but are not truly so. Key exchange. An important concept in any discussion of encryption is what we call as key exchange. Historically, the challenge has been that to get a secret, you must share a secret. Consider a simple analogy of a password as the key. Imagine that you are friends with a kid who requires a secret password to gain secret access. Perhaps the password is, open sesame. The problem is that at some point, the secret password has to be shared with you. This process is likely not going to be secure and will be subject to eavesdropping. Even if the password were whispered to you, it would still be overheard. Another challenge is that you and the kid have to meet face to face, so you will likely receive the key out of a band instead of when you're waiting at the door to gain entry. Modern cryptography solves the age-old challenges of key exchange. Exchanging keys in many applications happens securely in-band when you need to establish a secure session. Any type of out-of-band key exchange relies on sharing in advance, which means the key is delivered outside the network or process from which it will actually be used. Symmetric algorithm. Symmetric algorithm is a system that uses a common shared key between the sender and the receiver. The primary advantage of such a system are that it is easier to implement than an asymmetric system and is also typically faster. However, two parties must first somehow exchange the key securely. Like assume for example that you have a friend located thousands of miles away from you. To exchange secure messages, you send messages back and forth in a secure lockbox. You both have a copy of the key to the lockbox. This works, but how do you secretly or securely deliver the key to your friend? However, the key must have been communicated or delivered to your friend, which introduces additional challenges or logistics and ways to ensure that the key is not compromised in the process. So here, asymmetric cryptography helps overcome these challenges. Now imagine a system in which more than two parties are involved. In this scenario, every party participating in communication must have exactly the same key to compare the information. If the key is compromised at any point, guaranteeing a secure connection is quite impossible. Symmetric key algorithms are often referred to as secret key algorithm, private key algorithm, and shared secret algorithm. Symmetric key encryption uses two primary types of methods for encrypting plaintext data. First is stream cipher, right? So with the stream cipher, plaintext bits are encrypted a single bit at a time. These bits are also combined with a stream of pseudo-random characters. Stream ciphers are known for their speed and simplicity. Next are block cipher. With a block cipher, plaintext is encrypted in blocks, which are fixed length group of bits. A block of plaintext is encrypted into a corresponding block of ciphertext. For example, a 64-bit lock of plaintext would output a 64-bit clock of ciphertext because most plaintext does not fit within the precise block size. Leftover text is padded to complete the block. Let's talk about asymmetric algorithms. An asymmetric encryption algorithm has two keys, a public key and a private key. The public key is made available to whoever will encrypt the data sent to the holder of the private key. Now, the private key is maintained on the host system or application. Often, the public key encryption key is made available in a number of ways, such as through email or on centralized servers that host a pseudo address book of published public encryption keys. One challenge, however, is ensuring the authenticity of a public key. To address this, a public key infrastructure is often used. A PKI uses trusted third parties that certify or provided proof of key relationship or ownership. Asymmetric algorithms are often referred to as public key algorithms because they use the public key as the focal point for the algorithm. Now let's talk about elliptic curve and emerging cryptography, or ECC. ECC. The two other crypto systems are ECC, or elliptic curve cryptography, and still emerging quantum cryptography. ECC is a public key crypto system based on complex mathematical structures. ECC uses smaller key sizes than traditional public key crypto systems. As a result, it is faster and consumes fewer resources, which make it more ideal for mobile and wireless devices. Unlike elliptic curves and other crypto systems, quantum cryptography does not rely on mathematics. Instead, it relies on physics. Although this crypto system is smaller, its primary advantage is security. Quantum mechanics protects against data disturbance because no one can measure the quantum state of the protons. The mere observation of a quantum system changes the system. Now, what is a session key, or what are session keys? Session keys, sometimes called our symmetric keys, right, are randomly generated keys for performing both encryption and decryption during the communication of a session between two parties. Such a key is described as being symmetric because it is used for both encryption and decryption. Now, when a session key is generated, the key is valid only during or that one communication session. As a result, you can think of a session key as being temporary for one-time use. Additionally, a session key is deleted after the communication ends, but the key exchange mechanism used to establish the session often relies on a private key. This can be web server's private key, which is used to establish a secure session with the client. Although this is efficient, and the challenge is that gaining access to the server's private key allows an adversary to decrypt the communication. The benefit, however, is that the organizations can use this private key so that security systems, like for example IDSs and web application firewalls, have visibility to this traffic. Non-repudiation and signature. Non-repudiation is intended to provide for encryption a method of accountability that makes it impossible to refute the origin of data. It guarantees that the sender cannot later deny being the sender and that the recipient cannot deny being the recipient. This definition, however, does not factor into the possible compromise of the workstation or system used to create the private key and encrypted digital signature. The following list outlines 4 key elements that non-repudiation services provide on a typical client-server connection. First is proof of origin. The host gets proof that the client is the originator of particular data or an authentication request from a particular time and location. Proof of submission. The client gets proof that the data, or authentication in this case, has been sent. Proof of delivery. The client gets proof that the data or authentication has been received as well. And a proof of receipt, last one. Again, the same thing, the client gets proof that the data or authentication in this case has been received. So here, digital signatures provide integrity and authentication. In addition, digital signatures provide non-repudiation with proof origin. Although the authentication and non-repudiation may appear to be dissimilar, the difference is that with non-repudiation, proof can be demonstrated to a third party. Now let's talk about hashing. A hash is a generated summary from a mathematical rule of algorithm that is commonly used as digital fingerprint to verify the integrity of files and messages. Hashing ensures message integrity and provides authentication verification. In other words, hashing algorithms are not encryption methods, but they offer additional system security via a signature for data to confirm the original function. A hash function works by taking a string of any length and producing well-fixed length string for output. Keep in mind that hashing works one way. Although you can create a hash from a document, you cannot create a document from the hash. If this all sounds confusing, the following example should help clear things up. Suppose that you want to send an email to a friend and you also want to ensure that during the transit the message cannot be read or altered. You use software that generates a hash value of the message to accompany the email and then encrypts both the hash and the messages. So when the email is received, the recipient software decrypts the message and have the hash and then produces another hash from the received email. The two hashes are compared and a match indicates that the message was not tampered with. Because of the sensitive nature of cryptography, using well-known proven technologies is crucial. Backdoors and flaws, for example, can undermine any encryption algorithm. Vendors might have their own encryption solutions, and most of them depend on well-known time-tested algorithms. You should be skeptical of any vendor using a proprietary and proven algorithm. The following is a summary of this, right, on and other good practices. Use well-known and approved cryptographic algorithms. Adhere to required minimum key guidance for the chosen algorithm. Choose approved cryptographic modes and use strong random number generators. Let's talk about steganography, a method commonly used for obfuscating data or hiding data, particularly in media types such as media, video, image files, and other documents, is called steganography. Steganography is a word of Greek origin that means hidden writing. It involves hiding messages so that unintended recipients are not aware that there is a message. Compare this to cryptography, which does not seek to hide the fact a message exists but just makes the message unreadable by anyone other than the intended recipients. Writing a letter using plain text but invisible ink is an example of steganography. Let's talk about cryptography use cases. Cryptography has many potential use cases, and the following are the common examples. First is confidentiality. It ensures the privacy of data, right? And this is the most common use case, or at least the one that many tend to think of during discussions on cryptography. Next is integrity. It ensures the accuracy of the data. Hashing, as discussed earlier, is a common mechanism to ensure integrity. Assurance of message integrity, right, for example, might apply regardless of whether a message was encrypted. Non-repudiation. It ensures accountability so that the origin of the data cannot be refuted. Non-repudiation is needed to affirm the authenticity of a digital signature and verify that a message was indeed sent by the originator. Port 1 is authentication and ensures the secure transfer of authentication data between two entities or systems. Cryptographic authentication protocols are required for authentication. In addition, encryption and authentication work together and both have their own responsibilities when it comes to securing communications and data. Emerging solutions like homomorphic encryption are attempts at providing alternatives to working with data in processing and would allow operations such as searching and sorting to be performed on ciphertext as if it were a plaintext. Strong cryptographic implementation demonstrate resiliency to leakage and subsequent attacks, and research and development into highly resilient cryptography or leakage resilient cryptography is continuing. Like, for example, the physical implementation of cryptographic algorithms could leak information which can be leveraged to break the system. Let's talk about the cryptography constraint. Security systems often require trade-offs, right? Cryptography, for example, consume resources in system and carries a cost, right? Like security and performance and power all needed to be factored in. Modern computer systems and algorithms work well together. Furthermore, cryptographic implementations have made management easier, and in fact, more than half of the web is now encrypted using HTTPS. Now, when it comes to modern cryptography, performance and security have always been two important factors. How is it possible to increase the security robustness of an algorithm or a system without sacrificing speed and introducing more latency? Recently, especially with small and low power devices, the trade-offs and resources constraints are continually being considered in the search for lighter weight cryptography. Alright, and that's the end of the lesson. Here we spoke about cryptography, covering crypto systems, proven technologies and implementations, steganography, cryptography use cases, and constraints. Thank you very much.